So I changed the title of my project. It's now investigating polytartaric acid as the ideal binder for silicon anode lithium-ion batteries using DFT-based calculations. My name is Ryan Tay, and I'm from Jericho High School. I'd like to thank my mentor, Maura Appleberry, for helping me with my project. And let's get started. Silicon anodes will revolutionize battery technology. Current graphite anodes are expensive, ineffective, and bad for the environment. In contrast, silicon is much more promising as an anode material because it has a theoretical capacity 11 times that of graphite. It's abundant and it's not bad for the environment. However, a major drawback of silicon is that it expands when cycled, which reduces the capacity significantly. Figure 1a represents a pristine silicon anode without binders before cycling, but figure 1b represents the same binder after cycling, where silicon molecules have expanded significantly, distorting the anode. In contrast, figure 2 shows the cycling of a silicon anode with binders, and there is no major expansion. This is why an effective binder is needed. Last year, I created a neural network to identify the optimal chemical structure of binders. I was able to find that the algorithm ranked existing experimentally tested binders based on predicted performances, as well as determined chemical compositions of novel binders. One such novel binder was polytartaric acid, or PTA, due to its abundance of polar functional groups. While PTA is difficult to synthesize and electrochemically test, chemical simulations can be run to determine whether or not PTA has promise as a binder for silicon anode batteries. Specifically, mechanical strength, adhesion, and binder electrolyte reactivity are properties that have been proven to indicate capability as binders. That's why this year I was able to determine the adhesion, mechanical properties, and electrolyte reactivity of the novel PTA binder and 5 other common binders using density functional theory-based simulations. Density functional theory, or DFT, is a quantum mechanical theory that states that chemical properties of molecules can be determined when examining molecular orbitals. In summary, can adhesion, mechanical properties, and electrolyte reactivity show that PTA is a novel promising silicon anode candidate. In order to achieve my research goal, I looked at all 3 chemical properties, mechanical strength, adhesion, and binder electrolyte reactivity, for all 6 binders, PAA, PBDF, GG, SA, CMC, and PTA, using a DFT simulation. Then, I was able to predict whether PTA was a promising binder candidate based on how its chemical properties compared with the chemical properties of other binders. First, I simulated mechanical properties using a software called Abacus. I created imaginary silicon anodes with different binders, and I exerted a specific amount of force to replicate the conditions of silicon expansion. In order to run the simulations, Young's modulus and Poisson ratio were necessary for each binder material. However, since PTA has rarely been tested, its mechanical properties were determined using values obtained from equation 1, and specific thermodynamical constants used in equation 1 were determined by the DFT software WebMo. After running the simulations, a constant known as the deformation factor was provided by the simulation. Binders with a low deformation constant were more resistant to stress than were binders with high deformation constants. PTA had a significantly lower binder simulated. PTA had a significantly lower deformation factor, and except for when compared to guar gum, but figure 5C shows that guar gum, or GG, ended up taking on a weird dome-like appearance, while figure 5F shows that PTA responded in a uniform manner. This means that while GG was more resistant to the stress, PTA exhibited better elasticity, which is also an important mechanical trait. Therefore, it is reasonable to conclude that PTA exhibits better mechanical properties than all previously tested binders. Next, I simulated the adhesion of different binders to the surface of silicon particles. To do this, I looked at the relative adhesion of the binder and SiO2, since SiO2 is found on the surface of silicon particles and enables strong hydrogen bonds to form with the binder, as shown in figure 6. A metric used to measure adhesion was interaction energy, which measures the stability of a system with by subtracting a system with both binder and SiO2 from a system with just the binder and just the SiO2, as shown in in equation 2. Again, these values were all calculated using WebMo. Because the position of SiO2 relative to the binder is significant in influencing interaction energy, I showed only the positions with the highest interaction energies in figure 8. In addition, the relative interaction energies each binder can be seen in figure 7. Clearly, PTA and PAA both have significantly higher interaction energies compared to the other binders. This is because both PTA and PAA have a high amount of carboxyl groups. A possible reason for this is that the carboxyl group performs a special interaction that allows for stronger binding. When I investigated the molecular orbitals of PTA, I found that a shared unoccupied orbital was formed between silicon and carboxyl group, as shown in figure 9. This is likely an example of coordinate covalent bonding, which is why the interaction energy for PTA was so high. This binding also occurred in PAA and is noticeable due to the telltale bending of the normally linear SiO2. Therefore, PTA exhibits similar adhesion to PAA, which was the best tested binder. Finally, reactivity to electrolyte is a crucial factor in determining the effectiveness of a binder. The main factor that dictates whether electrolyte will decompose is the pH of a binder. An acidic binder will cause the electrolyte to decompose faster, while a basic binder will slow down decomposition. The specific reaction mechanism that causes the breakdown of the electrolyte can be seen in figure 10, but all you really need to know is that the acidic binders will eventually cause the consumption of lithium ions and speed up the silicon expansion. The pKa of different binders were retrieved through an online database, while the pKa of PTA was calculated using WebMo again. The pKa of different binders was observed in figure 11. Despite PTA, polytartaric acid, having acid in its name, PTA is actually a polyester, meaning it exhibits weakly neutral properties. In addition, PVDF and GG both don't have ionizable groups, meaning that they have a neutral pH. However, lacking ionizable groups makes these binders harder to form bonds. That means that PTA has the highest pKa of any binder with ionizable groups. Yeah. Oops. In my study, I showed that PTA exhibited better mechanical properties than any previously tested binders in literature. PTA and PAA both created unique bonding with SiO2, indicating strong adhesion, and PTA had the highest pKa for any binder with ionizable groups. It is reasonable to assume that PTA is a better binder than current commercial options, since it exhibits better chemical properties than all previously tested binders. Because I showed that PTA had promising chemical characteristics, this means that not only can PTA be applied for future silicon anode binder studies, but also that neural networks are effective in predicting novel materials. Finally, for future studies, I plan to apply neural networks to other aspects of battery science, physically test PTA for chemical properties, and electrochemically test PTA to see its effectiveness as a binder. Thank you for listening to my presentation. Here are my sources. Are there any questions?
Great job, Ryan. My question for you, now that you've given your whole self to this research and done such a thorough job, what is your dream career? And does it relate to this research? Is this sort of on the side? Where will this take you?
Well, I eventually hope to become like a researcher myself at like a university. So, and I hope to continue like my field of research, although it may not have to do specifically with silicon anode batteries. I do hope to stay in the field of battery research.